So, hi guys! Good morning! So, I am Syra Cantal. Tapos ang mga kagrupo ko ay si Shaira Mendoza, Laika Mercado, Erica Ferrer, at Emma Concepcion Lacorte. So, yon. Lacorte Manzano pala. Yon. So, we will tackle the, our topic. Our topic for today, 5.2. Nakapaloob dun ay truth tables, equivalent statement, at tautology. So guys, hope to enjoy the tutorial video.
So in this video, we are going to tackle about the equivalent statements. The two statements are equivalent if they both have the same truth value for all possible truth values of their simple statements. Equivalent statements have identical truth values in the final column of their truth tables. The notation P is equivalent to Q is used to indicate that the statements are P and Q are equivalent. This notation is used to say that the P and Q statements are equivalent. I will explain this with the truth value. So I have here a 7-column truth value, and here is the statement P and the statement Q. Let's say we have the statement P, which is true, and statement Q, which is also true. Another one example is true of statement P and false for statement Q. The otherwise false for statement P and true for statement Q. And lastly is false for both statements. So we have here the P and Q. So let's have here true and true, which give us the true. And if we have one false in either statement, we will consider it false, because remember, a conjunction must also both be true. So here we're going to have false, and this one is false. So next is the negation of P and Q. So here we will take the opposite of this one. It is the negation of P and Q. So we have here true, so it will give us false. False will give us true, true, and true. And our fifth column says that not P, not. So this will mean that P will be the opposite of this one. So we have here P as the base statement is true, then let us have here false. We have here false, and here we have false, then it will be true. And here we will also consider this one, which is not Q. The opposite of this one is false, true, false, and true. So here at our last column, we will consider this not P and not Q. So as the opposite of this one, it will give us false. And if we have here false and true, we will consider it to be true. So true and true, and both true will give us true. So finding the equivalent of the truth table, we notice that this column and this column have the same values. So we will consider it to be the equivalent statements. So we will write that as negation of P and Q is equivalent. So remember that this 3 bars sign is the equivalent to this one, negation of P or not Q. So that is simply how to use the truth tables to determine the equivalent statements.
Today is about tautologies and self-contradictions. First, let's define the word tautology. A tautology is a statement that is always true. While self-contradictions is a statement that is always false. Always remember that tautology is true and self-contradictions is false. Let's give some example. Show that P or not P or Q is a tautology. Let's make a table. Where we're able to put the P, the Q, P or not P or Q. We put that because that is the variable that is in the table. We said that under the P is the true, false, false. Well done Q, T, false, T, false. In P, so if you notice, we just copy it because P is always true. We notice that it's not P, so it's the inversely of the true. You notice that all of that will be answers true since the true is present on the both equation. Just we need to copy that Q. You notice, if there's a true, the answer will be true. Since in this equation, there's no true, so the answer will be false. Both sides are true though, so true. True, false, it's true. The table we make, it shows that P or not P or Q is always true. Thus, P or not P or Q is a tautology.
So next proceed to next topic, which is switching network. In a closure table, we use a 1 to indicate that the switch or switching network is closed and a 0 to indicate that it's open. That is example of negation closure table. Shows a switching network that consists of the single switch P and a second network that consists of the single. In a negation closure table, it shows a switching network that consists of the single switch P and a second network that consists of the single switch not P. The table below shows that the switching network not P is open when P is closed and is closed when P is open. Next, proceed to next switching network, which is series network closure table. It shows switches P and Q connected to form a parallel network. The table below shows that this parallel network is closed if P is closed or if Q is closed. Then, the parallel network. It shows that now consider the network shown to determine the required conditions under which the network is closed. We write first a symbolic statement that represents the network and then construct a closure table.
So let's proceed for the next topic,